Hi, my name is Molly Chhabra, and I'm a junior at Mason High School in Mason, Ohio. Today, I'm presenting VagusSync, a project focused on developing a closed-loop neural interface for tachycardia reduction in patients with POTS. In 2026, we live in an era of unprecedented biometric visibility. We have millions of people wearing smartwatches that can detect a heart rate spike with medical-grade accuracy. Yet for a patient with POTS, that data is often dead-ended. Imagine a patient whose heart rate jumps from 70 to 140 beats per minute just by standing up to hug a family member. Their watch knows it, their phone knows it, the data is screaming at the body in crisis, but because there is no closed-loop interface, the body stays in that crisis. Why don't we have that closed-loop system? To understand this project, we first have to understand the glitch affecting up to 3 million Americans suffering with POTS. Imagine your body is a car. For these patients, the fight-or-flight system, otherwise known as the sympathetic nervous system, is like a gas pedal that's stuck to the floor. This is sympathetic overdrive. When they stand up, their heart rate spikes to over 100 beats per minute because the brake pedal, known as the vagus nerve, has failed. The wiring of their autonomic nervous system is effectively cut. The current standard of care is medication like beta blockers. But beta blockers are a blunt instrument. They just slam the brakes on the heart, often leaving the patient fatigued. Instead of drugging the heart, why don't we hack the nervous system to manually engage the brake pedal? Existing vagus nerve stimulation uses electricity, but electrical shocks are painful and difficult to calibrate. This brings me to vibrotactile stimulation. By using precise mechanical vibration, I can activate the nerve without the pain of electrical shock. This brings me to my overall goal, to design a closed-loop system that detects tachycardia and manages it using a comfortable vibrotactile device, acting like a pacemaker for the nervous system. This closed-loop system must detect an overdrive state, then deliver a Goldilocks frequency vibration to the ear, and finally autonomously stabilize the heart rate. To achieve this, I broke my project into 3 engineering phases: mechanical design, electrical circuit and simulation, and optimization for the device. Starting with phase 1, my primary constraint was anatomy. The device must stimulate the symbiconcha of the ear, which is rich in vagus nerve endings. The criteria for success were consistent contact with the skin, patient comfort for long-term wear, and mechanical stability so that the device couldn't vibrate itself out of the ear. I utilized Fusion 360 to model 2 form factors, a behind-the-ear design and an over-the-ear design. I selected my over-the-ear model because it utilizes a 2-point hold system, an arm providing an inward push force, and neodymium magnets, ensuring the earpiece remains flush and against the symbiconcha, shown here. A critical part of the engineering process is predicting failure modes. I performed finite element modeling via end topology to analyze the natural frequencies of the device. I compared 2 materials, silicone and PLA. The results were definitive. With the over-the-ear restraint only, both the silicone and the PLA bodies were unstable at lower frequencies from 6 to 58 Hz, meaning they would displace during operation. The PLA body and silicone body, when restrained by the magnet and arm, remained stable up to 910 Hz and 108 Hz respectively. Consequently, I chose the PLA body with silicone housing to ensure the device remains mechanically stable during the 1 to 60 stimulation range required for therapy. Moving to phase 2, I needed to select a vibration source for my design. Current taVNS devices utilize ERM motors, which are the little buzzers inside your cell phone. Yet these operate more uncontrollably and in the 130 to 200 Hz range. Unlike a spinning motor, the piezo expands and contracts with microscopic precision, allowing me to generate specific frequencies between the ideal range of 20 to 40 Hz. The piezoelectric actuator is also ultra-light and small, fitting perfectly into the earpiece. While a standard motor runs on just 3 volts, the piezoelectric actuator acts like a capacitor. It needs a high voltage, up to 60 volts, to expand the ceramic layers and generate the necessary force. A standard wearable 9-volt battery cannot drive this alone. To solve this, I designed a circuit that uses a 9-volt lithium polymer battery and a voltage booster to step up the power to 60 volts. Then, a signal modulator carves that raw power into specific frequency pulses. Building this physically without testing is dangerous due to the high voltage, so I used LT-Spice to simulate the circuit's physics. The simulation results were successful. As shown in the green and red trace on the graph, the voltage booster successfully steps the 9-volt battery up to a stable 45 to 60 volt output. This high voltage allows the actuator to receive a 27 micron displacement and generate over 1 Newton of force in order to successfully activate the nerve endings. The most innovative aspect of this project is the digital twin. Because I cannot ethically test on humans yet, I needed a way to validate the closed-loop system. I created a virtual model that mirrors a device plus patient system, shown here. This required translating 2 biological processes into electrical behavior models in LT-Spice. The first is the McNeil model. With the goal of determining recruitment density, or how many nerve fibers are activated by the piezoelectric actuator, this model predicts how different patients might respond to the same vibration based on their unique nerve depth and density. The second is the Gersh-on-Duchamp equations. These model the cardiac response, simulating how the release of acetylcholine slows the heart rate. This allowed me to create a schematic where the electrical circuit, or the device, talks directly to the neural model, or the patient. By integrating these, I successfully simulated the full loop. A smartwatch detects a heart rate spike, triggers the microcontroller, which then powers the piezo, that then releases acetylcholine, and successfully drops the simulated heart rate. The simulation on LT-Spice shows the system autonomously stabilizing the heart rate. This is shown in the bottom window here, where the heart rate decreases as acetylcholine concentration increases, as shown on the window right above it. This simulation validates the feasibility of the control logic. In Phase 3, I addressed patient variability. Not every patient is built the same. A device that works for one person might fail for another due to differences in nerve sensitivity or anatomy. To solve this, I initially ran 850 digital twin simulations using what I call the static nerve activation model. In this setup, I randomized patient, mechanical, and electrical factors, but I treated the nerve recruitment as a fixed static value. 4 machine learning algorithms were tested, specifically XGBoost, LightGBM, Random Forest, and Ridge Regression, to predict the percent heart rate drop. The data were split into training and test sets. Independent variables were the patient, mechanical, and electrical factors listed here. The top performer was XGBoost. Even with this initial static testing, the model achieved an R-squared value of 0.92, accurately predicting the heart rate drops with a mean absolute error of less than 1%. This gave me the confidence that the digital twin was generating valid, predictable data. However, the feature importance analysis of the static model highlighted an interesting perspective. As you can see on the chart, nerve recruitment density was by far the most critical factor, accounting for 30% of the model's decision-making. This tells us that in our simple modeling world, biology is playing the biggest role. If a patient has more nerve fibers activated, the device works better, but with my device, I cannot change a patient's biology. I looked at the controllable factors, and stimulation frequency was the primary driver among them. But I knew the static view wasn't the whole story. Real human tissue is complex, it isn't static, so I revised the McNeil model to include the dynamic nerve recruitment. I added 4 different factors to advance the digital twin: mechanical to neural coupling of generated force and displacement, viscous tissue damping, where the ear tissue acts like a shock absorber, damping the vibration before it hits the nerve, spatial blurring, which accounts for the depth of the nerve in the tissue. The signal blurs and weakens the deeper it has to travel. And I added sigmoid fiber recruitment, showing that a nerve isn't a simple on and off switch. It follows a sigmoid or an S-curve. You need to generate enough force to cross the threshold and recruit enough fibers to actually trigger the baroreceptor reflex. If you only recruit 5% of the fibers, the brain ignores the signal. This model calculates if we are hitting that critical mass. A typical number for cardiac reflex activation is at least 40 to 60% of the fibers towards the top of the S-curve. In the dynamic model, nerve recruitment increases and decreases with the pulsed force and displacement. So, the model depends on frequency of vibration, amount of displacement force generated by the device, and anatomy and neurophysiology of the patient. This model gets us closer to reality, though still a simplification of actual neurophysiology. To run this dynamic model, I expanded the dataset with new independent variables that define patients' unique anatomy and neurophysiology. Nerve depth, showing how deep the nerve is buried, skin impedance, showing the resistance of the skin to the signal, fat thickness, showing that fat acts as an insulation and blocks the mechanical wave, and coupling, showing how efficiently the displacement translates into force. I ran a second set of around 600 simulations varying these specific anatomical parameters to see if the device could still cope with these variables included. As expected, with the more complex reality, the prediction difficulty increased slightly, but the XGBoost model still performed reliably with an R-squared of 0.87. Unlike the static model, where biology was most important, in the dynamic model, engineering has to work with biology to reduce the heart rate. Look at the top 3 factors: stimulation frequency, max displacement that affects nerve recruitment, and the target voltage that impacts both the displacement and force produced by the piezo actuator. The next 3 are the patient's sensitivity variables: optimum stimulation frequency range or standard deviation, vagal sensitivity defining how the heart reacts to vagal stimulation, and the Goldilocks stimulation frequency for the patient. This proves that starting with a responsive patient who has thick tissue or deep nerves, we can overcome these anatomical barriers by tuning the piezo behavior, specifically the frequency and displacement of the Goldilocks range of the patient. Finally, using the partial dependence plots from this dynamic data, I determined the optimal design window. These plots show the sweet spot for device parameters. For stimulation frequency, you can see a clear plateau of high effectiveness between 20 and 35 Hz. Below 20 is too weak, above 35 the effectiveness drops. For max displacement, we see a sharp jump in effectiveness once we exceed 10 microns. We need at least that much movement to activate the nerve. For max force, the curve flattens out after 0.8 to 1 newtons. We need to hit that threshold to trigger mechanoreceptors. Finally, for silicone stiffness, there's a distinct peak around 75K to 80K newtons per meter. This stiffness, roughly that of a phone case, is perfect for transmitting the vibration without absorbing it. These parameters match accurately with my prior literature review, confirming that my digital twin can successfully tune the device to maximize efficiency despite complex patient differences. To conclude, VagusSync validates all of my engineering goals. I established that a piezoelectric-powered taVNS device acts like a sniper shot compared to the blunt instruments used in current solutions. It delivers precise mechanical stimulation while the PLA body ensures that it remains stable in the ear, overcoming the tissue's natural damping. The closed-loop simulations prove that we can create a digital twin of the patient device system. This virtual model doesn't just run blindly. It autonomously stabilizes tachycardia, acting like a thermostat for the autonomic nervous system. Next, by applying AI to this data, I tuned the critical electromechanical factors. The model identified a Goldilocks frequency range, which matches the most promising literature data, confirming that targeting a frequency of 20 to 35 Hz provides the most reliable heart rate reduction. Most importantly, this project offers a path towards drug-free future. It provides POTS patients a viable alternative to fatigue-inducing beta blockers and painful electrical shocks to manage their symptoms. Of course, every computational experiment does have its drawbacks. Currently, these recommendations are only based on mathematical models and simulations. They require experimental verification to be clinically valid. Additionally, the earpiece is patient-specific, meaning one size does not fit all, and would need to be iterated. However, the approach of using a closed-loop digital twin has been successfully defined. Looking ahead, the next steps involve physical validation. This includes 3D printing the design for fit and comfort studies, building the physical circuit on a breadboard for electrical validation, and eventually moving toward testing on human subjects. I would like to thank Dr. Ward and the team at Purdue University's Department of Biomedical Engineering for their mentorship, as well as my father for his guidance on the electrical and machine learning components. Thank you for your time. I hope VagusSync paves the way for a future where millions of POTS patients have a comfortable, wearable, and drug-free solution to manage their condition.